All right, welcome back. So we followed sound waves all the way into the inner ear, where they're making the basilar membrane vibrate. But now we're at the most critical part of the whole journey, transduction. Seriously, this is where the real magic happens. It's the moment a physical vibration gets turned into an electrical language that our brain can actually understand.
So that brings us to the big question, right? We've got motion. The basilar membrane is literally wiggling, but our brain doesn't feel wiggles, it reads electrical signals. So how do we get from one to the other? How does our ear turn a simple physical movement into a complex neural message?
Okay, let's dive into that mission, from motion to message. And the heroes of this whole story are these tiny, highly specialized cells. Their entire job is to pull off this incredible conversion. Without them, hearing just wouldn't happen.
And here's their job description, plain and simple. These inner hair cells have one of the most amazing and vital jobs in our entire body. Take the physical dance of the basilar membrane and translate it into electrical sparks for the auditory nerve. This is the exact point where the physics of sound becomes the biology of how we perceive it. It's incredible. It all starts with this beautiful microscopic dance. It's a completely mechanical thing at first, involving the different membranes in the inner ear and these unbelievably tiny hair-like structures. So, let's take a look at the choreography.
So check this out. As the basilar membrane moves up and down, it creates this kind of sideways shearing motion against the membrane that sits on top of it. You can see it right here. And that motion causes these little bundles of hairs, they're called stereocilia, to get pushed and pulled, making them sway side to side. And it's that simple bending motion that kicks off everything else. Now, what's truly mind-blowing here is the scale we're talking about. For a sound that is at the absolute quietest limit of what a human can possibly hear, the distance these little hairs bend is just 0.3 nanometers. I mean, that is an unbelievably small distance. To try and wrap our heads around that, let's use this amazing analogy. Imagine one of those tiny stereocilia was somehow scaled up to be the size of the Willis Tower in Chicago. Well, the amount of movement needed for you to just barely hear a sound would be like the very top of that skyscraper swaying by only 5 centimeters. That's about 2 inches. That is the insane level of sensitivity that's built right into our ears. So how on earth does a movement that tiny lead to anything at all? Well, for that, we have to zoom in. I mean, way, way in, down to the molecular level. We're about to see the incredible biological machine that turns that tiny, tiny bend into a huge electrical event. It all happens in this super fast 4-step chain reaction. First, as we saw, the stereocilia bend. That bend pulls on these tiny little connecting threads, stretching them out. That stretching motion pulls open these molecular gates, or channels. And finally, boom, charged particles called ions rush through those open gates. It's like dominoes falling. Each step immediately causes the next one. Let's look a little closer at how this works. Those little threads are called tip links. You can basically think of them as tiny ropes tied between each of the stereocilia. So when the hairs bend, the ropes get pulled tight. And what are they pulling on? They're pulling on what are pretty much molecular trapdoors. These are ion channels right in the cell's membrane. The tension from the tip link literally yanks that little trapdoor open. And the moment those trapdoors fly open, positively charged potassium ions, which are all over the place in the fluid around these cells, just flood into the cell. Now, a cell is normally in a negative electrical state. This sudden rush of positive charge causes its electric potential to shoot up. And this critical change has a name. It's called depolarization. And this is it. This is the moment. We have officially converted a mechanical force into an electrical change. That electrical change, that depolarization, is the trigger for the grand finale. It's what allows the hair cell to finally talk to the nervous system. It's what creates the very first spark of a neural signal that's going to head to your brain. And this diagram just shows those final steps perfectly. The depolarization of the cell makes it release a chemical messenger, a neurotransmitter called glutamate, right at its base. You can think of it like the cell gets electrically excited. And because it's so excited, it tosses a chemical note over to its neighbor. So that neurotransmitter crosses a tiny, tiny gap called a synapse over to a waiting auditory nerve fiber. And when it gets there, it triggers that nerve to fire an electrical signal of its own. And that's it. That is the spark. That's the neural spike. It's the official, translatable message that's now going to travel all the way up the auditory pathway to be interpreted by your brain as sound. Now, really quick, it's super important to clarify something. We actually have 2 different kinds of hair cells. The inner hair cells, the ones we've been talking about,
are the messengers. They do that critical job of transduction. But the outer hair cells, they're the amplifiers. They can actually change their own length to help fine-tune and boost the vibrations of the basilar membrane. They're crucial, but they aren't the ones sending the main message to the brain. So let's just end with this thought. This whole incredible process, from a microscopic bend to an ion channel opening to a neurotransmitter being released to a nerve firing, it doesn't just happen once in a while. It happens thousands of times a second, for every single frequency and every single sound you hear, all day long. So what does it tell us about the hidden, mind-boggling complexity of our senses that this elegant process is happening right now deep inside your ear?